Hello everyone, welcome to the course on electromagnetic theory and interference. In this session, let us see how to find the input impedance of a transmission line by using the Smith chart. So here a lossless transmission line with the characteristic impedance is at not 50 ohm, having a length of 30 meter is given and operating at 2 megahertz. The line is terminated with a load impedance of 60 plus J40 ohm, and the velocity on the line is 0.6 times the speed of light. So we are asked to find the reflection coefficient, standing wave ratio and the input impedance. We already know how to find these parameters without Smith chart by using the formulas, right? So this is the formula which is used to compute the reflection coefficient ZL minus Z0 divided by ZL plus Z0, and after using the calculator converting rectangular to polar form, we get the magnitude and angle. For the VSWR, that is standing wave ratio, it is 1 plus magnitude of the reflection coefficient divided by 1 minus. And to find the input impedance of the line, characteristic impedance, load impedance is known. We need to find what is beta L. Beta L is the electrical length of the line. Beta is nothing but omega by U. Length is given as 30 meter. So we have to convert that 30 meter in terms of degrees, right? So omega is 2 pi f. So 2 pi into frequency is given, length 30, velocity is 0.6 times the speed of light, that is 3 into 10 power 8. So the beta L is 120 degrees. So taking tan of 120 degree, we are having this answer. After converting into rectangular form using the calculator in complex mode, we get the answer in ohms. So without using these computations, let us see. These are the given data, right? ZL, Z0 is given. Length of the transmission line is given. We are supposed to find the input impedance. Apart from the length, frequency and velocity also given. That is not mentioned here. So let's start doing using the Smith chart. Here, in all the problems that we are going to look upon, first we have to normalize the load impedance with respect to characteristic impedance. So 60 plus J40 have to be divided by the characteristic impedance 50, and after dividing we get the answer in terms of R circle and X circle. So we need to find 1.2, that is R circle value, and the X circle which is nothing but 0.8. The intersection of these two circles is the point P where the normalized load impedance is present. After that, taking OS center and this OPS radius, we have to draw a circle using the compass. This circle touches the real part of the reflection coefficient axis, okay, at S equal to 2.1, because here it is 2, 3 and each division is 0.2. So this is the standing wave ratio. Now let us find the reflection coefficient. To do that, we are going to extend this OP line to OQ, where this Q is a point where it touches the innermost circle, right? And if you could take the ratio of OP by OQ by using a scale in centimeter, we get its magnitude. To find the angle, we already know the angle of reflection coefficient is given in the scale, right? In the protractor scale. So here it started 0, 10, 20, 30, it goes on like this. Our value is present between 50 and 60, exactly at 56 degree. So we are able to find that is angle of SOP, this angle only. To find the input impedance, that is Z in, we have to first express the length of the transmission line, which is 30 meter, in terms of lambda or in degrees. So it will be easy to work with lambda. So we are converting into lambda here. So we know the relation between wavelength and frequency. It is velocity by frequency. So that is equal to 0.6 times the speed of light is given, divided by 2 megahertz is given in the question. So we get 90 meter. If 90 meter equal to 1 lambda, what about the given length 30 meter? So that is equal to 0.333 lambda. So we have to move from this load location towards the generator in clockwise direction as mentioned in the scale, okay, to reach the generator, so as to find this input impedance. So if we add these two distances, we get 0.505 lambda. Since the maximum distance that we covered in the Smith chart is 0.5 lambda, so the value is greater than, the arrived value is greater than 0.5, so we are subtracting from that and we are getting 0.005 lambda. If you closely observe the scale, this horizontal line is 0 lambda, right? and after that the first scale is given as 0.49. That this is the scale for wavelength towards load actually. Above that, wavelength towards generator scale is there, so it should be 0.01 lambda. Okay, and this will be 0.02. Here it will be 0.03. Here it is given 0.04 lambda above. Since I have highlighted here, it's not visible. So 0.005 lambda will be located here, half of this value. Here it is 0.49, that is 0.01 lambda, half of here. So we have to draw a straight line connecting this point towards the center, and wherever this straight line cuts the VSWR circle, that point is G. So we have to find at the G location what is the resistance circle passing, what is the reactance circle passing. Since it is lying above, it is a positive reactance. So if you could see here at G location, we can see it is 0.48 because it is 0.5 here, this exact line. Before that only it is occurring. 0.48 is R circle. X circle, if you could see, it is meeting the third line. Here it is 0.1. So each should be 0.01 value for the X circle, right? So it is 0.03. So to find the actual input impedance, we have to denormalize. Already we have normalized and plotted, right? We have to denormalize by multiplying with the characteristic impedance. So 50 into whatever value we got in the Smith chart. So everything multiplied together, we get the input impedance in terms of ohms. And here in this problem, we can find one more data that is not asked in the question, that is load admittance we can find, YL. Already we have plotted normalized load impedance, right, ZL. So quarter wave length, this is a quarter wave length. Complete circle is half wavelength. This quarter wave length will convert impedance into admittance. So we have to just extend this PO line to PO P dash, and wherever this is meeting this constant VSWR circle, at that point we are able to find the normalized load admittance. Okay, here if you could see, it is given below 0.6, that is 0.58, and since it is located below, we have to take the reactance as negative. If you could see here, it is lying above 0.4 in the first scale, so that is 0.38 minus J. 0.38 is the normalized load admittance. And if you want to find the original load admittance, we have to denormalize by multiplying with characteristic admittance. Characteristic admittance Y naught is nothing but 1 by Z naught. So we divided by Z naught and write the answer in ohm inverse. So these are the complete solution. Z naught, ZL, length is given, frequency, velocity of the line is given. So we converted length in terms of lambda, and we have found the input impedance. And rest the reflection coefficient. There is another way to find the VSWR and magnitude of reflection coefficient. Since these two scales, SWR is the first scale given and towards the left hand side of the Smith chart, and in the third scale we can see reflection coefficient E or I is given here. Okay, so we have to draw a straight line connecting the VSWR circle to the scale. Only towards the left hand side the scale is available, so we can draw a straight line, and wherever the straight line is touching these scales, we can see the SWR value is 2.1 closely it is same. Based on here also we can find it is 2.1. okay, wherever it is meeting the real part of the reflection coefficient axis, that is also 2.1. Here also scale it is same, we can cross check. Similarly, magnitude of reflection coefficient, we took the ratio of OP by OQ by using our normal scale, right? That we can cross check by here also. It is lying in between 0.3 and 0.4, that is 0.35. So same, it is closely resembling the same. Angle have to be found from this protractor scale only. That is, this is SOP, the angle between these two. Okay. Hope you understood how to find the input impedance VSWR and reflection coefficient of a given transmission line of a particular length. So happy learning. We will meet in the next session by seeing how to find the location of Vmax and Vminimum.